Hello students, in this video we are going to determine the net charge of a given pentapeptide at a given pH, in this case pH 11, and we have to also determine its isoelectric point, okay, pIE. Actually this video is a continuation of the previous video number 39, where we determine the sequence of a pentapeptide from its tandem mass spectrometry data. Okay, so now we will now first determine the net charge of this pentapeptide at various pH values. So in order to study that, we have to study the effect of pH on ionizable groups on the peptides. You see, the ionizable groups, like the free amino group on the N terminal, the free carboxyl group on the C terminal, and you also could have potentially on the side chains, you could have polar ionizable groups, the carboxyl groups, amino groups, etc., etc. Okay, they could also be influenced by the pH. So the ionizable groups on the peptides can be classified into two chief types: acidic C terminal COOH, side chain COOH. Okay, C terminal COOH is for any amino acid that occurs on the C terminal. Then side chain COOH for amino acids like aspartate, glutamate. Side chain alcoholic groups like, or phenolic groups like in tyrosine, serine, threonine, and thiolic groups like in cysteine. Okay, now you got the basic, some of the amino acids are basic groups like the all the amino acids. Okay, if they are on the N terminal, okay, on the N terminal they got the free amino group, so that is going to get influenced with the pH. But other than that, some amino acids have got side chain amino groups like in lysine, side chain guanidino group like in arginine, which is a very strong base, the guanidino group. Okay, and the side chain imidazole group like in histidine, even though histidine the pK value is quite close to 7. Okay, anyway, all right, that can be either a proton acceptor or a proton donor. So that but for now, okay, we take this imidazole side chain as a base. Okay, all right. Now, what are the states of these acidic and basic groups? See, depending on the pH of the surrounding medium of the peptide, the acidic groups are chiefly in two states. Okay, let us take the example of the carboxyl group. It can be either the deprotonated protonated COO minus form or in the protonated COH form. Okay, all right. The deprotonated form has got a -1 charge, and the protonated form has got a 0 charge. The basic group, okay, the basic groups like amine group, if you take an example, that can be the protonated NS3 plus state as well as the deprotonated NS2 state. The NS3 plus state has got a +1 charge, and the NS2 state has got a 0 charge. Okay, so that's how the basic group exists at various pH. Okay, and what happens? What is the underlying principle here? If the pH of the medium is greater than the pK of a particular ionizable group, then the particular group on the peptide is predominantly in the deprotonated form. Okay, all right. If the pH is greater, okay, the amino group will now chiefly exist in the deprotonated form, NH2. For example, the carboxyl group will be in a deprotonated form, which is CO minus, right? Similarly, if the pH of the medium is less than the pK of a particular ionizable group, then that particular group, ionizable group on the peptide, is predominantly in the protonated form. Okay, so the NS2 group, amino group, will be NS3 plus form. Okay, and the carboxyl group will be unionized COH form. Okay, with no charge. So that's how we have to look at it. Okay, so now, and that's also for the other groups also. Okay, so now we will look at the pentapeptide at hand. The pentapeptide at hand that we saw in video number 39 was glycine at the N terminal, followed by phenylalanine, followed by glutamate, followed by threonine, followed by methionine at the C terminal. Okay, so this pentapeptide has the following ionizable groups susceptible to pH. Of course, the terminal NH2 group that is attached to the glycine, and the terminal carboxyl group that is attached to the methionine. Okay, other than that, okay, you got glutamate that has got an acidic COH group, right, on its side chain, and also threonine that is actually got a weak acid, okay, weak acid, alcoholic acid, weak acid group on its side chain. Okay, all right. And other than that, glycine does not have any side chain ionizable residue, so also phenylalanine. Okay, and so also methionine. Okay, on the side chain there's nothing there. Okay, so now if we have to look at the pK values, the free NH2 group at the N terminal glycine has a pK of 9.60. Now when I say the pK value, it's for the conjugate acid NH3 plus, so that has got the pK value of 9.60. The free COOH group at the C terminal for the methionine residue has got a pK value of 2.28. The side chain COOH group of the glutamate residue has got a pK of 4.25, and the side chain OH group of the threonine has got a pK of 13. Okay, all right, it's a very weak acid, so that's why its pK is very high, pK of 13. Okay, now let us look at the table. Okay, we'll make a table, and we are looking at the states, at the state of these ionizable groups at various pH. We'll start from pH 1. At pH 1, all the groups are protonated. Okay, so the glycine terminal amino group is in the +1 NH3 plus state. Okay, so it's got a charge of +1, and the glutamate, the threonine, as well as the methionine C terminal carboxyl group, they are all unionized in 0, 0, 0 charge. So the charge, total charge is +1. Now what happens in pH 3? What happens? The pH, becomes greater than the pK value of the terminal methionine group or terminal methionine carboxyl group. So it gets deprotonated. So it gets a charge of -1, and the other groups remain the same, and the total charge becomes 0 of the pentapeptide. At pH 5, what happens? Compared to pH 3, the glutamate also gets deprotonated. Glutamate side chain COH, because that now the pH has gone above 4.25. Okay, so what happens? That also loses the proton, gets a -1 charge, and the total charge of the pentapeptide becomes now -1. Decreases by 1. Okay, from 0 it has become -1. Okay, at pH 7, everything still remains the same. Okay, and the charge is still -1. Okay, now we go to pH 11. What happens is the glycine N-terminal amino group, which is protonated in the NH3 plus form, that becomes deprotonated to the neutral 0 charge NH2 form. Okay, and what happens here? Okay, the other chains remain the same, in the same state whatever they were in the pH 7, and so now the charge becomes -2 at pH 11. Okay, and at pH 14, even the threonine weak, the weak acid alcoholic threonine group, that also loses the proton, and the total charge becomes -3. Okay, so from this table we can see that the charge of the pentapeptide at pH 11 is -2, right? Total charge. Okay, now to calculate the pIE, the isoelectric point is the pH where the net charge of the peptide is 0. Okay, we can see from the table that the peptide transitions from a net charge of +1. Okay, if we go back, we can see that the peptide has a charge of +1 at pH 1, and the peptide has got a charge of -1 at pH 5. Okay, all right. So what does it tell us? Okay, somewhere in this range the pH becomes 0. So as an approximation, okay, the pIE is taken as midway between this pH 1 and 5. So this is calculated as an average of these two pH values. In this case, pIE 1 + 5 by 2 is equal to 3. Okay, the average is 3. So the isoelectric point is approximately 3. So this is an approximate value. The actual isoelectric value should be done experimentally. Okay, so even if you go back to the table, okay, if you go back, we can see that at pH 3 the total charge is 0. Okay, but we have to actually do the calculations to get the isoelectric point. Okay, so thus we can see the total charge of the peptide at pH 11 is -2, and the pIE of this pentapeptide, of this given pentapeptide, is 3. Thank you. Have a nice day. Bye.